So generally, that's kind of the most important thing we saw in the previous video, how to take two equations and two unknowns and solve them. And I always went back to the graph as well as doing the algebra. And we want to ask, will this always work? Well, there's two important special cases where things get weird. So here I just changed the top equation. The bottom equation is the same. I changed the top equation. And the first thing I'm going to do is I'm going to graph that. You don't absolutely have to, but boy, you get a pretty good intuition right away from graphing this thing. If you graph that carefully, what you notice is that these are parallel lines. And they're perfectly parallel. We'll check that in a second. And so they don't have any intersection. There is no point, so there's no pair of x, y values that satisfies both these equations because it would have to be on both those lines, and they're parallel, okay? And so that means the way we say that in sort of algebraic language is this is an inconsistent system. There is no solution. And we're done. You don't try to find one anyway. You just say, there is no solution. We are done. Don't try to find one. And how would we have been able to tell this in advance? And how could we be really sure that they're perfectly parallel, not just seemingly parallel? Because we don't want to trust the graph there, okay? And we can do that by finding the slopes, okay? We know exactly when two equations are going to be, two lines are going to be parallel. It's if they have exactly the same slope. So that's 12y equals 4x plus 6. Just don't bring that over. Divide by 12. And then we get 1/3 x plus 1/2. Okay, and let me just remind you, this one was 3y equals x plus 3. Divide by 3. Aha, there's that 1/3 x plus 1. Okay, so these are exactly the lines with exactly the same slope and different intercepts. Yes, they're perfectly parallel. There's no solution whatsoever to these guys. So if you suspect that a system might be inconsistent, calculate the slopes of both lines. Not hard. You probably want to do it anyway. It's really what you would do to get a careful graph, and you're going to see it. You're going to see, oh, these are inconsistent. Okay. If you ignore the possibility and you try to solve these guys, I recommend always checking first before trying to solve. But what happens if we just actually tried to solve? For example, with the elimination method, I'm going to multiply, so I'll show you, let's multiply the bottom one by 4. And then I'm going to subtract the second equation from the first. So that's a little trickier than adding, but I'm going to take a minus of all this stuff. And so I'm going to take minus 4x minus a minus 4x. That cancels. That's exactly the point. And then I'm going to have 12y minus a 12y. Whoops. This is weird. But then I have 6 minus 12 on the other side. Wait a sec. I'm saying that this only works if the number 0 is equal to the number minus 6. That's impossible. Don't circle that and say, oh, I've discovered a new truth about math, that the number 0 is equal to the number minus 6. It's saying that this is impossible. The logic is technically that you're saying if there were an x and y pair that satisfied both of these equations, it would only work if somehow in math 0 was the same number as minus 6. But we know that's not true, and so there is no solution. Not surprising, since we already had a couple of ways to see why there shouldn't have been a solution. So if you're doing elimination and things get weird, don't just fudge it and say, oh, I guess that's true, blah, 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 right? Just recognize that it's telling you, yeah, this is impossible. And then go back and really double check and go back and say, hey, wait a minute. Let's go back to the actual original equations. What are the slopes of these lines? Are they the same? Oh, gosh, I should have seen that, right? But it's okay. Okay, one more case. Very similar, okay? Still the same second equation. And now I've only changed the right-hand side from this second version that we had, okay? Let's see what happens when we graph that. I'll let the computer do it, just be quick. Whoa, the computer seems to have screwed up. I asked it for 2 lines. It's only drawn 1. Well, here's the deal. Let's look at this equation, okay? If I take that equation and I divide everything by 4, oops. Oh, that's just the same equation, okay? So this is a very special case, but it totally can happen. It's that you have two equations that seem to be different, but they're actually identical. Okay, this is called a dependent system. That sort of the one of the equations depends on the other. It's really just a multiple of the other. There's just one line. So actually, if you like solutions, this is great. But we usually don't like this case, actually. We usually like to have a unique solution. So this is not something people tend to like, but you get an infinite number of solutions. So any point on this one line works. Sometimes people or I might say, you know what, can you give me the simplest version of that line? If you're going to say everything on that line works, then let's go ahead and do what we've done a couple of times before, and oops, that's a plus, and just sort of solve for one of the variables in terms of the other. So that just makes it more definite, right? So it says, given any possible x value, calculate y as 1/3 of that x value plus 1, then this will be a solution pair. And because it's any possible x value, you're going to get an infinite number of solutions. You're going to get everything along that line. Okay, so how could we have told that a little bit earlier? Again, the slopes are going to be the same. These both have slope 1/3. And once you know that, you know you're either in the inconsistent case, where it's two parallel, distinct lines, or don't assume that. You might want to say, wait a minute, what if the slopes and the intercepts are equal, right? And if the intercepts are also equal, then we have a dependent system with infinitely many solutions. All right, so that's the quick and dirty rundown of these issues. And we'll practice this in class and see some word problems that address the same issues as well.